almost 40% of us will at some stage in our life be diagnosed with cancer. That means that some of your relatives probably has cancer or has had cancer, or that you have or will have cancer yourself. Almost everybody is affected somehow. If you look at the global population, almost 10 million people are dying from cancer every year. Now, if you compare that with COVID-19, COVID-19 is almost a year now, or more than a year now in the world, and 2.7 million people has been dying from COVID-19. 10 million people are dying from cancer.
In the last decade, the most important thing in cancer research is personalized medicine. So personalized medicine is when you're able to tailor the treatment to the individual patient. That would only be possible given a large amount of data.
If you start spreading data for research purposes, of course, you have the risk of revealing personal information about individuals that you're not allowed to do, that could harm people.
One of the vital things to move cancer research forward is this sharing of data, but the patient's privacy needs to be kept. And to do so, it's vital to be able to generate synthetic data. So this synthetic data needs to be so good that it keeps its clinical relevance, but the persons are anonymized.
We always underestimate how much is hidden in the data. It's a little bit like fingerprints. So actual fingerprints which we have on our fingers. They don't have our names, our addresses there, but we already understand, right? So there's a specific pattern which we have on fingers. It's unique enough so that the person can be identified. And with medical data and with other types of data, it's similar, only we don't realize it yet. So we have our medical records have enough unique information so that person can be identified from this data. And it should be hidden in the same way as we hide our fingerprints.
There is this one example that shocked me when I read about it. The case is in Australia, not very far ago, they released 10% of the healthcare records from their population. 10% of the population healthcare records were released. But of course, they removed all the personal information, maybe even added some noise. But it took the community of researchers only 6 days to re-engineer the data and get back the personal information. 6 days. 10% of the people of Australia's personal medical records. And this is what we want to stop. We don't want that to happen in Norway. We don't want that to happen anywhere.
Nextbridge is a consulting company where we help our customers within business intelligence, data warehouses, and artificial intelligence. So this project is actually perfect for us because then we can demonstrate our capabilities within this area.
Doing this project now with Amesto is to try to improve the availability of data to, in the first hand, get some access to synthetic data, which is not the real data, but something which is similar, so that you can do your primary hypothesis testing and so on these synthetic data outside of these very secure environments.
Our first start with this project was basically digging deep in journals, latest publications regarding GDPR and healthcare data, and see what kind of methods are out there, what can we use, and how can we use them to aid our goals.
In our view, the best way of generating synthetic data is through GANs. That's what we try to solve here in this hackathon, is the ability to take clinical data add some noise, go through a loop where we optimize and do better and better and better the ability to make good synthetic data.
These GANs usually work in tandem, so it's actually two neural networks that work together. One is starting off quite stupid and trying to create data. And the other network is saying, oh, this is good or bad. So I don't believe you, this must be fake data, and it tries again. So two networks work together in synthesizing the data.
It's a little bit like with face recognition, right? If we look like for 20 years ago, and you need to make a program which recognizes faces, right? So you maybe look at the distance between your eyes and the color of your eyes. You have the shape of the nose. You introduce these features, and then you compare the features of a real person to another real person, right? To see it's the same face. But what neural networks do today is a completely different approach. They don't use human-generated design features like the shape of the nose. They find features themselves which turn out to be optimal to discriminate and to say if these like two faces belong to the same person or to a different person. They do it by training on millions of faces, and they do it in an automatic way. So we don't need to use humans who decide which properties of the face are most important to look at, because we don't know which are most important to look at.
AI is, for some people, a buzzword, but artificial intelligence is actually helping us to see what is hidden in the data. You can use computers to browse through that information, find patterns, find segments, find things that you couldn't see with your own eyes or with traditional methods. And you can predict what is going to happen in the future with people based on what you see in the past. For instance, in chess, the computer starting beating people 10 years ago, and that was a revolution. Now computers are getting where they actually can understand texts, written documents, as good as people. When you can use artificial intelligence to solve chess problems and to understand texts, imagine how you can use the latest research to actually solve the cancer mysteries.
We're always looking to apply the best analytic methods for doing this research. We have done cancer research on epidemiological data with standard statistical methods for the last 70 years and discovered quite a lot of novel insights and how to prevent cancer, how to improve the cancer. But as the analytic methods improve, we need to employ those methods and discover new insights from the data. And AI methods are, of course, in the forefront here.
We know these data science techniques and machine learning and deep learning in depth. And this might be a great strength when it comes to collaboration with researchers, because this might not be their strength. They are subject matter experts in their own fields, in medicine or biology or even astrophysics, and we can help them with said machine learning techniques in aiding their goals in their field of research.
When you want to have a personalized medicine, you need to kind of know the tumor. You need to know what goes on in a tumor, what part of the genome of the tumor is amplified or deleted, what part of the tumor is mutated. And this knowledge can only be gained by analyzing a large amount of tumors. Some tumors are common, some cancer forms are more rare, and to have a large enough data set, you need to collaborate with other scientists to be able to characterize enough tumors for that specific cancer type so that you can be able to model its behavior.
I think the most fantastic thing about SAS is that you can have a platform where you can store data, and share it securely. And that's what we are aiming to do in this project. From a secure area within our health authorities, we have data that we cannot share. we produce a synthesized data that we can share outside the platform, and you can do some research on that, give it back to the platform and give it back to the researchers, and really see if the hypotheses you've made actually are working on the real data. And as a basis for this, we will use or are using SAS platform. SAS also is one of the most renowned statistical tools that exist in the market. And you can combine that with open source code as well, as we've done in our project.
Working with open source data and code is quite trivial. You have a code you have made and you have tested and it looks okay. You put it on the internet and whoever wants to use it can use it with a disclosure agreement. And the same is said with data. So if you have data and you want people to use your data, you can put it online and it is open source, and whoever wants to use it can use it with some limitations, of course.
Being in this hackathon is a very good opportunity for us. First of all, we have a lot of employees in Amesto Nextbridge that are, as a matter of fact, they are doctors within different areas. So they are used to doing research. And we are a commercial company. We don't do research anymore. So actually being able to contribute to the research community is of big value for our employees. So motivating our highly intelligent people with projects like this is one thing. Another thing is that if we solve this issue to create data that more people can research on, if we solve this, the people that are researching on cancer will have more data to research on because it's being spread more widely. And that way we can cooperate more and make this world a better place.
We have to synthesize our healthcare records so that more researchers can have access to the data, and we can use it to find new treatment methods and create better collaborations between partners and between researchers internationally without regarding and without breaking GDPR.
If we now get a very user-friendly way of creating synthetic data based on the real data, that would improve and probably speed up the research process in medical research on cancer.
After doing our analysis on the test case, we can see that we are able to both keep the scientific relevance in the data set, but also see that the personal information is lacking from the data. And that is our goal. So I think we have actually done it.
Personal information is not only about diseases, it's also about us as people. Information about individuals. What we are doing in our team can actually contribute to helping to solve some of the mysteries of life. This project is a very good opportunity to do something for the greater good.